In this problem, we have a charged disk with some sort of radius r, but so make sure for it to be known that it's a disk and not a loop. I'm just going to shade it in right here. So we have some sort of radius r from the center all the way out to the edge here. So this is radius. So this is a capital R, and the reason why it's a capital R is going to be apparent whenever we start evaluating the integral. And we want to find the electric field at some point P above the charged disk, and that distance from the center to the point P is a distance z. So of course, whenever we start with our electrostatics problems that we have here, we'll just begin with the definition for the electric field in integral form. So we have some sort of an indefinite integral, and then now we're just listing off the things that we're going to try to hunt down. So this is dq right here. So of course, if we want to find the electric field at some point P, we're going to have to draw some vectors, and I'm going to go ahead and just use red here and maybe some darker ones. So let me see. So if I do from the center all the way out to some part of that charged disk, that little vector right there, that is the separation, or the vector that points to the contributing, one small portion of the contributing to the electric field. And then from here all the way up, that's just going to be r. And of course, our separation vector between that contribution chunk from the disk to that point that we're going to have is the separation vector r. Before we jump too far into it, I'm just going to go ahead and just let's say we just blow up this sort of piece here. So instead of little infinitesimally thin chunks that contribute to the electric field, we have little chunks of the disk here. And so, of course, since we have some sort of polar symmetry here, we're going to use some polar coordinates where our origin's right at the center of the disk, and they are vector points, of course, radially outward. We have some sort of phi, and then we have a z-axis right here. So looking at this charged piece of disk here, right here, of course, just from review, we know that this length is going to be r d phi, where r is just some sort of random distance. It could be here, it could be that length. It's just some variable length for the radius here. And then this distance here is going to be dr. And of course, the area of this whole thing, dA, is just r d phi dr, right? And so that means that our dq is equal to, and we were given the surface charge density here is just sigma times dA, which is then we just plug in what we just determined there was a little r d phi dr, of course. So that helps us finding out what dq is. So we'll go ahead and put dq here. Of course. Next, we're going to go ahead and try to figure out what these vectors are here. So we'll just start with the, let's go ahead and do orange, be consistent. So the vector, the separation vector is, of course, it's always good to go just step by step, make sure that we're not going too fast and get lost here, is equal to, let's give us some more room, is equal to, so the this vector, the vector that goes from the point of origin to the place that we're trying to evaluate the electric field, that only points in the z direction, so it has some magnitude, variable magnitude z, but it points in the z hat direction always, and then it's minus, and then let's try to figure out what that vector is going to be for that vector that points from the origin to each contributing portion. As you can see, that always points from the origin outwards, right? So it's only going to be pointing in the r hat direction with some variable magnitude r. It's not going to be like a curving vector or anything like that. So we're lucky that we just get some variable magnitude, but direction r hat. And the next portion is we're just going to have to find the magnitude of that, right? So the magnitude of it, of course, thanks to Pythagorean's theorem, is just the components dotted with themselves, or the components magnitude squareds, all under the square root. Yeah, so it's just this length right here. And then finally, we find the unit hat vector for that separation vector, and that's, of course, the vector itself that's normalized by its magnitude here. And we just take these two things and divide them by each other. We normalize them. So we have a z hat minus r hat divided by the magnitude of all the components, right? Okay, we'll go ahead, since we're looking to substitute this and this in there, we luckily already have those two values, so we'll go ahead and just explicitly write them here in our steps. I'll start with the unit hat vector. All right, and next is the, let's see here, the magnitude of it. So just curly r is equal to the square root of what I just wrote about it. Here we go. We'll go ahead and take these and just make the substitutions in here. So all that is equal to, nothing changed with the constants. I'll just go ahead and ditto them down. And one thing that's important to note is that since we have two differentials right here, we're going to have to turn this into a double integral. The first one, the inside one's going to be phi, and phi ranges from 0 to 2 pi, right? So from where we want to start all the way around, once around the circle, so 2 pi. And then r starts from the origin all the way out to the radius of it, which was defined by its big R, so we have 0 to r. Go ahead and throw in our unit vector. And then finally, well, not quite finally, but next we'll do our r squared, so it's just going to be this value squared. Oops. There we go, in parentheses. And then finally our dq, which we'll throw it on top here. Okay, so the next step here is we're just going to go ahead and just do some more of the math here and just expand this out. I'll take each one of these integrals and chunks and just multiply them by each one of the subtraction here. So we're going to end up with two integrals, but I'll pull out the relevant constants up front. So times the big quantity of, we have a double integral. I'm going to forego writing the limits of the integral just for time. This one's going to be z. So that becomes to the the 3/2. This is all in the z hat direction here. Minus, and we have a whole nother integral here with the sigma r squared this time. Z squared plus r squared to the 3/2. And this one points in the r hat direction, getting a little crowded, but that's okay. So we have two components. We have a z hat and r hat. This is where a lot of the symmetry comes involved. If we look back over at our diagram here, we know that wherever each one of these contributing vectors to the electric field from some chunk of the disk is going to have some sort of z component, but it's also going to have some sort of r component. And every single one, thanks to symmetry, every single component that we have here, every contributing factor to the electric field is always going to have an equal and opposite r hat direction. So we know just from inspection and by symmetry that we can just go ahead and throw out all of the r hat terms. So since these are all the z hat terms, this is all the r hat terms, we can go ahead and just drop that double integral, which is always nice to drop a double integral. And then all that's left is, I'll just go ahead and write it out explicitly, 0 to r, 0 to 2 pi. And now we have our, let's go ahead and pull out some constants out in front. So the sigma doesn't change, the z doesn't change, and the z hat doesn't change because we're not doing any integrals in terms of z hat. So that's all that left is r d phi dr, and then under r, z squared plus r squared to the 3/2, right? And in the z hat, which is over here. All right, so next portion that we're going to do is just going to go ahead and just evaluate this d phi integral. Since there's no phi variables in here, it just ends up being multiplied by 2 pi. Scroll up a little bit, so we have pi epsilon naught. Now we have a single integral from 0 to r, and we had a 2 pi that was evaluated, so 2 pi was thrown down. We still have our r dr, and then we have our z squared plus r squared 3/2 here. Okay, and as you can notice, we have some terms that we can cancel out here, so I'll go ahead and do that. It's going to be interesting because these will end up coming back later on, and I'll tell you why. So this is going to be 2 right here, and the pi's just cancel out. So next we're going to go ahead and just look at this dr integral. This isn't going to be as easy as the phi integral, but that's okay. So one other thing that's important to know, and I'll keep saying this, is you'll end up working with these integrals so much you'll end up memorizing them, but until we get there, I'll go ahead and just explicitly write them out. Excuse me, there we go. So what I'm writing right now is just a general integral for some constants d and c, an integral evaluated at x over x squared, within the 3/2, and that's always going to be equal to the magnitude of that constant that's under the integral minus the square root of all that stuff that was under the 3/2, but evaluated at d. Well, d and 0, but yeah, you guys get what I'm saying. That ends up being here, so this ends up being d squared. So if we apply this kind of integral table result general form to what we have, this integral that we have here, what we're going to end up having is something a little bit more manageable to work with. Just go ahead and write the constants out here times the quantity of 1 over z. Z is always going to be positive in our case. So, not necessarily always positive, but we can always adjust it as needed. The variable always captures the term, so we evaluate it there. And then we just pull out, just because of convention, we always just throw the z hat out here. So that actually is our integral. That's our one part of our end state right here, is that we just found that the electric field at some point z above a charged disk that has some radius r, and then some sort of charge density sigma. But the question asks us to do a little bit more analysis here, so I'll just go ahead and write this one out explicitly. So when r is much greater than z, so basically, let me go ahead and just rewrite that disk here. When this radius is much greater than the distance z, so if I just go ahead and write that z, so if it's so big that it just looks like this point just keeps getting closer and closer because z just keeps going further and further out, right, and just getting bigger and bigger and bigger, ends up taking up the whole page. What ends up happening is that r is going to look like infinity. It's going to look like just a giant endless wall. And so we can go ahead and apply that to what we have right here. This is a good leap pad for more interesting cases, and this is always a good way to check your work and kind of understand what I like to think of like the elegancy of physics. Always works in the extreme cases. So we still have our sigma, we still have our z, we're just rewriting what we had up above here, right? Except we're just applying what we had over here. So if r is looking like infinity, this term, this is infinity squared, which makes this whole thing look like infinity, and then 1 divided by infinity, something extremely large, is just going to be 0, right? And then whenever we look at all this, we can go ahead and just evaluate it as exactly equal to, these ends up canceling out, sigma 2 over epsilon naught, and this is in the z hat direction. I dropped the z hat, my bad, but yeah, so that's an important thing. That is, if we look in the textbook, that's a portion that was noted in there. This is the electric field for an infinite wall, for a point near an infinite wall. It's not going to vary with z, because no matter how far away you get from an infinite wall, it's always just going to look like an infinite wall, no matter how far away you go. So that seems to make sense. But we also have another case for us to look at. When r is much less than z, or if z is much greater than r, so that just kind of means that if we have that that disk, and we just keep moving the charge further and further away, it's going to look smaller and smaller until all the way out here. And the charge is just going to look smaller and smaller. Eventually, two things are going to happen. At some point, it's just going to look like another point charge. This disk is going to look so small that it's just going to look like another point charge compared to this point here. But if we also keep going, it's going to end up being like this little charge is going to end up looking like nothing, and we're going to get essentially no contribution to the electric field. So we expect two things to happen. So I'll go ahead and talk about the most extreme case right now, where we move so far away that essentially we don't measure any electric field, or at least that's what our intuition says. And we'll just go ahead and make sure that aligns up with our mathematical understanding of this model. So whenever that happens, Z is approximately goes off to infinity, right? Or it's approximately infinity. It's approximately very, very large. So whenever we do that, as you can see here, whenever we compare it to the other terms, R is going to look like 0 compared to a very large number. So it'd be Z squared plus 0, right? And then whenever this happens, this entire term right here goes to 0. You could look at it either way, like 0 going off into infinity, right? So both of these terms isn't going to 0. Or that R looks like 0 compared to Z. So this ends up being 1 over Z, and then 1 over Z minus Z. But this term still stays the same because we're not really comparing it to anything else. So whenever we have that happen, this entire term goes to 0, and so our electric field goes to 0. I guess technically in the Z hat direction. Right, that makes sense. Like we said, the further away we take this point, if we go further enough away, it's just going to look like a point in space with some sort of disk infinitely far away, and it's going to look like we're going to have no contribution to the electric field. But the other case, and the final case that we make, is that whenever we move this point further and further away, eventually it's going to look like that little disk is just going to look like a little dot compared to everything else. So this should eventually, somewhere in between infinity and where we went before, it's going to end up looking like a point charge. So we'll just go ahead and do this second case over here. All right, for the second case, and this is a little bit more involved, but we'll just go ahead and rewrite everything out. This second case, we still have 1 over Z. We'll still keep this form. And what I'm going to do next is just kind of change the form of our 1 over square root that we had over here. Change it to, Z squared plus R squared to the negative 1/2. This is still in the Z hat direction. Right, and we haven't made any approximations yet. This is still equal to. I'll let you know when the approximations happen. So we'll just keep this chunk of constants the same out in front. This is still 1 over Z. All right, and we'll do 1 minus, I'll take a 1 over Z out of all this stuff. So we have 1 plus R squared over Z squared, still to the negative 1/2, all in Z hat direction. All right, this is where the approximation happens. So like I said, what's happening here is that we're taking this disk, we're doing some approximation where this is essentially really far away, right? So really, really small contribution, but we don't want it to be small enough so it ends up going to 0. We still want to evaluate the value at something close to 0, but not quite at 0. So that really tells us and hints us at a binomial expansion, right? And this is relatively easy. This is a relatively easy one. So this value, and if we do a binomial expansion, this is going to end up being 1 plus the value that was within this portion right here, 1 plus this value, so this is R squared over Z squared. And then the coefficient is going to be the coefficient of the square root sign that we originally had here. So that's negative 1/2 right here, right? So we just apply this to this value right here. What we get is the same glob of constants, 1 over Z minus 1 over Z times the quantity of 1 minus 1/2 of the 1 minus r squared over z squared, and quantity, and still in the z, pointing in the z hat direction here, right? And so what we end up having is we'll just do some algebra over here. So z, rewriting out all of our values here, times the quantity of 1 over z minus, and just go ahead and multiply this into our terms. Whoops. Minus 1 over z plus 1/2 r squared over z to the third, all pointing in the z hat direction. Seems to make sense so far. All right. And then what we're going to do is, of course, this all stuff goes to 0. So I'll just go ahead and cancel out those terms while we're doing everything. And then when this z comes in and hits this thing, this ends up becoming 2, so it's z squared. And next, let's go ahead and explicitly write all this stuff down. Is that, let's see here. We'll have a sigma over 2 epsilon naught times 1/2 r squared. Let's see here, r squared, z squared, pointing in the z hat direction, right? Okay, so at this point you might be wondering, what in the world, how is this supposed to mean anything like a point charge? Well, if you remember, if we go back up to this point where we had some pi's and we canceled out those pi's, if we go back there and we bring those pi's back, so pi over pi here, you'll see something interesting happen. So if we go ahead and just distribute those pi's back to their customers, right? So and we apply the algebra, we have 4 pi epsilon naught, the 4 coming from, of course, the 2 2's right here, 4 pi epsilon naught, and that's being multiplied by sigma times one of those pi's, r squared, and you might already be figuring out where I'm getting at. All that's left off in the denominator is z and times the z hat. And if you recall, this chunk of stuff right here, dq, is actually equal to dq, where dq is our surface charge density times the surface area is actually equal to, that is the circumference, or pi r squared right here. So what we have left is the a formula for, or the expression for the point charge with some sort of charge q, which is the charge that is on our disk and points in the z hat direction, which is exactly what we thought would happen. At some point in between going off to infinity where this looks like 0, this is eventually going to look like a point charge if we move far enough away, but close enough that we still want a value close to 0, and that's where our binomial expansion came out. And technically, actually, this is where we made the approximation here.